it's Coach Fred here, and so hopefully you've learned about polynomials in your class, or if you're in my class, I know you have, and therefore you've learned about long division and synthetic division. Well, there's a couple other theorems that come into play when we're talking about long and synthetic division and polynomials that are really useful and helpful. And so remember, theorems are things that we prove. We learned about that in geometry. Well, in this case, I'm actually not going to prove the theorems to you. I'm going to show them to you, and we're going to apply them. Now, there is a way that I can prove them to you, but I'm just not going to do that in this video, okay? All right, so the first big idea is the remainder theorem. The remainder theorem says that when we divide any polynomial, okay, and so when we divide a polynomial, say p of x, could be f of x, p of x, doesn't matter, by x minus c, some linear factor, okay, the remainder is actually going to be p at c. Okay, now what I've learned over the years is that you guys don't really like reading theorems the way they're written, right? Because what is it? It's all that math mumbo jumbo. Okay, so I'm going to put this same theorem. I'm going to give you an example. So if I divide, here I give you this polynomial, f of x equals x to the fourth minus x squared plus 2. And I want to divide it by the linear factor x minus 1, okay? Then the remainder is going to be f at 1, whatever f at 1 is, okay? So let me show you what I mean. If I use synthetic division really quickly, I'm going to find the remainder because I want to prove it to you, okay? So I'm going to put in 1 in my box, and I'm going to use my leading coefficient. So here I would have 1, 0, because there's an x cubed missing, negative 1, 0 for the x, and 2. Okay, those are my coefficients. Bring down the 1. So 1 times 1 is 1. Add down. 1. 1 times 1 is 1. Oops, put 1 here. So we're going to add down. We get 0. 1 times 0 is 0. 0 plus 0 is 0. 1 times 0 is 0. So I can see that my remainder here is 2. Okay? Well, let's just plug in 1 and see what we get. Well, if we plug in 1, 1 to the fourth minus 1 squared plus 2. So 1 to the fourth is 1. 1 squared is 1, so minus 1 plus 2. So 1 minus 1 is 0, and so you can see that's my remainder. So this is just actually really useful if I just am trying to figure out what the remainder is, okay? Now that also tells me that the point 1, 2 is actually on the polynomial x to the fourth minus x squared plus 1, right? My input was 1, my output was 2. All right, so we could evaluate this. We could evaluate this function with long division, synthetic division, or we can plug it in. So f at, so negative 4 cubed minus negative 4 squared plus 13 times negative 4 plus 29. If I plug that in, I'm going to get my remainder. If I divide by x, the negative 4, if I divide that polynomial by x plus 4, I worked this out. I got negative 320 minus 16 minus 52 plus 29. So I got negative 359, okay? So the remainder theorem allows me to conclude that when f of x is divided by x plus 4, right, because it would be the factor, not the 0, when the remainder is negative 359, okay? You could use calculator and Desmos to confirm your result, right? It should tell you then that the point negative 4, negative 359 is actually lies on the graph, right? It should tell me that. It should also, remember, I could rewrite that as f at -4 equals -359. These are basically the same thing written differently. Okay, so what's the bottom line? The bottom line is we can use the remainder theorem to tell if a number is a factor, right? We don't need long division to do this. Now, you are going to need long division sometimes when you want to really be able to write a function in factored form. But if I'm just trying to tell if something's a factor, I can use the remainder theorem, okay? Because if the remainder were 0, then it would be a factor of the polynomial, okay? All right, hopefully that was a helpful video. Have a great day.